See, until now, our discussions have been limited to in-plane, orbital plane. Okay. What we're going to do is we're going to discuss a 3D perspective of orbits. Okay. So in that context, we're going to learn about different reference frames. The first one is called geocentric right-ascension and declination. So when you're talking about the right-ascension and declination, what do you understand from here? Anything you? Huh? It could be reading a map, but what should hit you is the geocentric. Geocentric means the reference frame is at Earth's center. Okay. So you have the sun. Okay. Right. We've just passed the autumnal equinox. I want you guys to do an exercise, okay? And this will give you some extra points. Tell me what an equinox is, okay, and a solstice. You don't have to tell it now. You can submit it as a, just write up. And these are specific dates, right? Huh? We just went through autumnal equinox, right? So you need to tell me what a solstice is and what an equinox is, and why is this summer solstice? Why is this winter solstice? Huh? Okay. It's a very interesting very interesting thing to know. So what plane is this? This plane or the board, what plane is this? What plane are we looking at? If you're looking at the board, what plane is this? This is the orbital plane. Orbital plane or ecliptic plane. And what is the other plane? See this direction? You see this direction? This, if you look at this, say it goes through the center. Okay. This is the north. Now, the plane perpendicular to this is the equatorial plane. Okay. If I redraw this perspective from, or this view from the perspective of Earth center, ecliptic. Alright. So try to see this from the, if this is ecliptic, what does this mean? So where is the orbital plane now? The orbital plane, it's perpendicular to this board, right? So you're actually seeing the orbital plane here like this, okay? This one, the orbital plane is you're seeing from the top. This you're seeing from the front. This is the front view, this is the top view. Make sense? This is the north-south direction. Okay? You know what this angle is? You remember what that angle is? This angle? What is the value of that angle? $33.5 degrees. So this angle is around 33.5 degrees, okay? So this is your, if this is your north-south, you remember, you have to know that the Earth rotates about this axis, right? And this axis is 33.5 degrees off of the angular momentum axis. This is the angular momentum vector. Make sense? What do you mean by precess or precess? Or let's say, what do you mean by accession? Do you know what accession is or declination is? Huh? Not precession, precession. Yeah. There's precession. Okay. No, that precision is Precision. That precision is different. You have precession, you have precision, you have precession. Okay. What is accession? Ascension or accession? Ascension is just going up, ascend, right? Declination is going down. Right. What is precession? So let's look at this geocentric right-ascension declination frame. Okay. What does this mean? You understand what latitudes and longitudes are? What are latitudes? So you have right-ascension. Accession is measured where is the 0 degree latitude? Is that the latitude or the longitude? That's the longitude. The 0 degree longitude is the GMT, right? Prime meridian. Now when you measure the angle right from that direction, that is your accession angle. Huh? So because you are rotating in that direction, Earth rotates from east to west, right? So when you measure that angle from 0 degree across your different longitudes, that is the right accession, and you're measuring it in the right direction. If you look at the north, you measure it in the right direction. It is right accession. Okay, so that is one of the directions. Just a minute, I'll come back to you. The declination is the angle measured from equator to declination is either up or down. Okay, so you have accession and declination. You have defined two angles. Now you can use this to define the position of any place on Earth using these two angles, right? And you can just, if you go from center of the Earth through that point, you can define the orbiting body, where that orbiting body is. So geocentric right accession. If you just say, for example, have you tried to track a satellite anytime? Probably not, right? Have you tried to track an aircraft anytime? If you have radar, so what do the radars do? They have azimuth and elevation, right? Rotors. So you have azimuth is, you do this. Elevation is, you do this. You see how you define those? Yeah, you do this and you do this. So with these two, you can pretty much say what angle, what right accession, and what declination your aircraft or spacecraft is. Correct? If you have that angle going through the center, you'll always know where your object is. So this is one of the reference frames. Make sense? So where is the reference frame is, the origin of this reference frame is center of the Earth. And where does, you have the vernal equinox. See this, what is this symbol? You follow astroscience? Or this, what is the symbol? This is the Aries, right? Aries is a constellation. This Aries constellation, with respect to the position of Earth, is always there. For that matter, any constellation around the equator, the constellations, the 12 constellations you have, or the 12 constellations for your star signs, are around the equator, right? All of the constellations are in everywhere else. But you always try to follow those 12 constellations, and that is the reason you have 12 star signs. this constellation Aries is the initial direction. It is the first day of spring. First day of spring, if you look in the direction of Aries, that would be your, and the north direction. So those would define your initial accession and declination. From that point onwards, you just keep on rotating. Okay? So if you look at Earth, this is the -0° meridian, and your angles, the angles along this, if you start from here, 10, 20, 30, 40, so on, okay, and you have, from here you have 10, 20, 30, 40, so on. So these angles are declination angles, right? That is what we discussed. This is the right-ascension because you're moving in the right direction. So what does this give you? You understand why we are discussing this? You get a feel for why we are discussing this. What does this do to an orbit? Or why is it important to orbital mechanics? But what are you trying to do here? Using these angles, see, if somebody asks you, where is the pencil sharpener in the school? Pencil sharpener. If you were, right? You can use something like this, right? You start here, you go X, Y. Or what you can do is, you can say, think about this as a sphere. So you can say, go, if this is, let's say, your 0 degrees, go 10 degrees or 20 degrees, right? And if this is your 0 degree meridian, you say 1, 2, 3, 4, 5, 6, it's there. So using this, you can define where your orbiting body is. From any position on Earth, you can just say 0 degrees and go this way. And if you define this radius is known, right? If you know the orbiting body, you can always define the position of the orbiting body. So that will give you where the orbiting body is. Make sense? This is one of the reference frames for defining the position of the orbiting body. You have to see, when you're communicating between teams, you need to set your clock to a origin, or you need to set your clock everybody has to start somewhere. That reference has to be the same. So if you're discussing with somebody in, let's say, Europe or India, right, you need to have a common reference frame to define where your objects are. You cannot use your own reference frame. You cannot say it's this much from you unless you define your own position and orientation. So this gives you that general reference frame to define the position of the orbit. So the next one we're going to look at is all right, let's stop here. Let's discuss a little bit about your exam tomorrow, Monday. Your exam will start at 7:45. Okay. I've sent you some outline as to what will be covered. You'll have numericals. You'll have manipulations, you have derivations. Okay. And derivations and manipulations, most of it has been covered in class. Okay. I'll try to provide you as much information as possible so that you don't have to. At least you'll know where to start. In every problem, you'll know where to start. I'll say starting with. Okay. You cannot, if you want to use calculators, you have to bring your own. You cannot borrow calculators. No cell phones. All cell phones will be switched off. No bathroom breaks. If you want, you have to use it before or after. Huh? See, there are certain equations which you need to know. No formula sheet. There are not many equations you should know. There are just a few. A lot of them are derivations. So and what happens is, what I've noticed is, if I let you have a formula sheet, you'll just get the derivation in your formula sheet. So, huh? Yeah. Huh? It's not slip simplicity. It will not be too long. The exam will not be too long. If you know your stuff, you should be able to finish it in 45 minutes. In 45 minutes. Half an hour, 45 minutes. Huh? Okay. And keep in mind, you will not have any take-home versions. Okay? If you do well, you score well. You don't do well, you don't score well. That's it. Okay? It's quite possible Many of you may not do well. All of you may do well. You have to remember that you have to give it a try. Okay, you have to give it a sincere try. Okay. Any questions? Any concerns? So chapter 1 and 2. Go through the example problems in chapter 1 and 2. I think that will help. Go through the homework solutions, homework problems. I wanted to give you guys the solutions to the homework, but nobody showed up that day, Tuesday. So.
What are your expectations for the test?
Score well. You have to see, there are two things, okay? I always look for one is effort and the other is competence. Huh? So you have effort and competence. If you cannot demonstrate both of them, then you are in trouble. Okay? It's not 9 o'clock yet. You're not supposed to have a meeting.